In the last video, we talked about the organic matter. Now we go to the rocks and fossils. We are talking about some matter with a long life, lifetime. In this case, we cannot use a carbon because the age of any rock will be many billion years. We cannot use a carbon with a many thousand years. We have to use another radioactive element of many billion years. In general, in this case, we can use another isotopes. For example, we can use uranium, rubidium, potassium with a long period. Okay, this method, I repeat again, we have two isotopes. We have two elements, parent and daughter, where the parent is an unstable element and the daughter is a stable element. Let me explain. First of all, we have to study the first method. We have to study the case 1. What I mean by the case 1, at a time t0, we have p0 and decayed atom, and we have 0 stable atom. It's important now. I repeat, we have p0 and decayed atom, and we have d0 stable atom. What I mean by this point, I mean with the time, all the produced stable atom come from the decay process from the unstable atom. Okay, we don't have initially any stable atom. This is the first case. I want to study this point. So we have parent unstable decays to daughter stable. We have P, I don't use N, okay, just P parent, D daughter. We have P and decayed parent element and D stable daughter element produced by decay, only produced by decay. The daughter element at a time t must be produced from the unstable element. Okay, so initially at time t0 we have p0 parent element atoms and we have 0 daughter atoms. At a time t, this parent atoms, the initial value will be divided between a remain quantity of remain atoms p plus the number of daughter atoms produced by decay. So p initial value at a time t equals to pt plus d at a time t. When I say star, it means this value is produced by decay. Pt is a number, the remains number of unstable element, and dt is a number of daughter element at a time t. Just a simple calculation. You know, P, we have to calculate, first of all, Pt by decay's law. Pt equals to P0 exponential minus lambda t. We can substitute the value of P0 here. Okay, here. So we get here Pt equals to pt plus dt times exponential lambda t. Okay, here just to simplify the relation, pt equals to pt plus dt exponential lambda t. I can put it down and we can change the sign to e lambda t. Just we put it like this. So we calculate 1 over e lambda t, which is equal to pt divided by pt plus dt. And we go to find, first of all, e lambda t. We can put it here. And this one, we can change the position of each term to get finally, dt divided by dt divided by pt equals to exponential lambda t minus 1. This is the first equation. You can use it directly, equals to the daughter atoms divided, the number of daughter atoms divided by the number of parent atoms at a time t, equals to the exponential lambda t minus 1. This is in the case of zero stable element at a time t0. So we can simplify the equation to calculate the age. Okay, so we can calculate the age, and simply this value dt divided by pt can be calculated by using a mass spectrometer. Lambda is given for the for any element, so we can calculate the age by this one. This is in the case if you know dt and pt, and we have zero initial value d0. What about the second case? Here we have p. Now we can calculate the age if we know the number of daughter atoms produced by decay, d star, and the number of parent atoms now present. Here we have an application to determine the age of rocks and fossils. We have a rock is found, contains uranium-238. Uranium, it's a radioactive element. It's a parent element. So the parent element, we can say PT, or you can say directly uranium at a time t. We don't need to put n, number of uranium at a time t. Anyway, you have uranium 238, and we have as a daughter element, it's PB 206. Scientists analyze, okay, they found the total mass of uranium at a time t equals to 2.4 gram, and also the mass of lead equals to 1.11 gram at a time t. We have to find the age of this rock. I give you lambda of uranium equals to 4.46 billion years. I mean 10 power 9 years. Okay. Lambda is for uranium. Lead doesn't have lambda because it's a stable element. Uranium is an decayed element. Okay, we can follow the same procedure. Pt equals to P0 exponential minus lambda t. Here we have uranium. In the place of P, we can put U. Ut equals to U0 exponential minus lambda t. And also U initial 1 at a time d, at a time t, will be divided between the undecayed atoms Ut and the daughter elements PBT. Okay, we did the same calculation in the last video. Here, simply, we put U0 by its value here. We get UT equals to UT plus PB exponential minus lambda T. We do the calculation to get finally this expression where PB divided by U equals to exponential lambda T minus 1. We calculated before D divided by P at a time T daughter divided by parent equals to exponential lambda T minus 1. And we can calculate the time. Let me do the calculation before. So first of all, I write again, we have PB at a time T divided by uranium at a time T equals exponential lambda T minus 1. We have to calculate lambda equals to ln 2 divided by T half. Okay, be careful. The unit will be years minus 1 or 1 divided by year. Okay, and also here, you know, we talked about this point. We can say the number of mole here, this one equals to number of mole times Na, and the number of mole equals to mass divided by M. Okay, so here we can substitute directly here. We can say number of mole times Na, or we can say mass of Pb divided by M times Na. Okay, it's Pb times Na. The same for uranium. Na divided by M. Okay. Anyway, equals to exponential lambda T minus 1. We can eliminate Na and Na. We have the value of M molar mass of Pb and molar mass of uranium. You have the calculation here. We have 205.9 the molar mass of lead and 238 is the molar mass of uranium. You do the calculation, okay? We get finally the age of this rock, okay? So here I can give you the mass of the indicate atom and the stable atoms. I can give you the activity, the number of mole, any one of these parameters will help us to find the age of rocks.